Hey guys, this is Shubham. I'm Shubham Agnihotri and I'm being a part of the Quantum Machine Learning Apprentice team. So here will be, there's a second, this 102 version of QML where we'll be discussing about QSVM, using kernel estimators. There's another way to implement it, which is using variational quantum circuits, which we'll be looking onto the 103 uh, section of it, which will be in the next session. So before we start, I'll just give a brief of what happened in 101. We kind of did, for the people who are new here, we kind of did just a brief intro on what exactly is quantum machine learning. Then, why do we need quantum machine learning? What all are the problems which it solves? Then we discuss on the applications of it. Then we also showed, there are a few algorithms which have been implemented, which is QSVM, we have QGANs, we have QNNs, we have QMeans. So as soon as we move forward in the sessions, we'll be discussing each one of them and we'll see how what are advantages it gives and what all benefits do we have from them. And yeah, so let's get started with today's session. So, okay. Quantum QSVM, which is quantum support vector machines, is a quantum implementation of SVM where it kind of tries to leverage the disadvantage that SVM currently is facing. SVM is a machine learning algorithm which was initially used for classification. Now it's used for regression as well, but the primary we used it for classification way, and it is used on supervised learning. So what exactly is supervised learning is we have a data set which is a labeled data set. So what do you mean by labeled data set? Means, let's say there is an image, it's of a cat, so the image is labeled as cat. Same goes, that is what supervised learning is. And so the task of the SVM was to classify whether this belongs to this category or that belongs to that category or something like that. So how SVMs work is, now, okay, I'll just show you. It's stop at its initial one. Yeah, something like this. Okay. So here we can see that we have data around here, and then we have some red points outside this region. So we need a function which can which needs to identify somewhat the middle section of it. But then again, we see there are some loop data points outside as well. So how do we do that? Because now this is not exactly circle in between. We have some data points outside as well, and even red is pretty much every is outside, whereas we have some blue points outside as well. So how do we solve such problem? So what the people did is we represent the data in we add new dimension to the data so that we represent it in a new form. New form means we add one more axis to it, which is the z axis. Now we can clearly see that eh, all the blue points lie somewhat down the plane or down the curve, and whereas all the red points lie somewhere up. And then there is a hyperplane. What exactly is a hyperplane? It's a plane which uh, classifies it into two segments, whereas the upper segment belongs to one class and the lower segment belongs to another class. So this is pretty straightforward. Whereas when this was just for a binary classification where we have two types of data, and here we have two, let's say two features, x and y, like two dimensions of the features. So once we go into much more detail, that means we have more number of classes and more number of columns, or we say more number of features. This is what SVM does. It kind of it becomes computationally expensive to try to find plane in n dimension to classify, and that is where we need something called as quantum SVM. which leverages the power of parallel computing through its properties of entanglement and superposition, enabling it to do things in parallel and make it give results in something real time, not real time, something in something which will not take years to do that, and with a great accuracy. So how quantum classification works is, by the way, in the meantime, if you have any questions, you can definitely post it in chat. I'll address them later after I complete the session, and even uh, I guess Shadab and KG can answer them in meantime if they want to. Yeah. So okay, how quantum classification exactly works now? If you attended the previous session, I told you that currently there isn't a way in which we can feed a quantum data directly to a quantum computer. So it either has to be generated inside a quantum computer, or it has to be a classical data. We can definitely generate a quantum data. What exactly the quantum data is? A data which is either generated in a quantum computer, or is the data which is collected by performing some quantum mechanical operation. So, but there is no way which we can directly feed a quantum data. So what we do is we generally take a classical data, and like we have classical data and we convert into quantum data, then we do some processing on it, and then we apply some measurements, and then we read the output. Okay, so how do we convert the classical data into quantum data? So that is where we have something called as quantum feature maps. So I've tried to keep this session very intuitive so that it's easy for everyone to understand. So yeah, so you might not see much of these formulas in the sessions, but if you want, I can explain it to you. So the yes, the V is stand for the circuit. Like everything in quantum is a circuit that you give a data point to a circuit. Like it's not in quantum, even in classical computing, it's a circuit. You give some values, it's performs some operations and gives the output. So we have the circuit. In between, it takes a classical function. What is the task of the classical function? It is applied on the classical data, and then this thing acts as a parameter to a circuit which converts it into a quantum data. So there are various feature maps available to us via which we can convert our quantum data to, classical data to quantum data. We have set feature map, we have ZZ feature map, and if someone wants to go a bit more in general, we have poly feature map. I'll be discussing them later in just five more minutes. So yeah. So what are the factors which decide a feature map? Now, okay. So to be very in layman terms, what I can say is a feature map is something which takes in data, classical data, and converts data into a state uh, which can be represented in Hilbert space. That means it converts the data into something, into quantum realm or something like that. So why do we need a quantum feature map? Exactly, why can't we work with a classical feature map? I read the research paper. What they say is, they're currently, they did not get any statistical advantage on using quantum feature map, but just because we don't have exactly you know decent amount of quantum computers to run that. But they strongly believe that definitely using a quantum feature map uh, will give us a much better advantage. Yeah, that is a problem currently with all the algorithms, because so all of things exist, but we are not able to implement them because we don't have the hardware to do that. So what are the main factors which are required to choose a feature map? Just give me a sec. Yeah. So there are basically four main factors. The feature map depth, circuit depth. What we can look at as, I always like to connect it back to neural networks. We have different types of layers, and consider, let's say, each feature map as a type of layer, and then depth can be, the layers, how many layers you stack. Let's say you have conv layers, so convolution layers, you need this much amount of convolution. Let's say two conv blocks or two dense blocks or something like that. So that is what depth means. Means we are trying to how many those circuits have to be repeated. Then data map function. So okay, one important thing is uh, the number of features your data set has. That many amount of qubits are required for our algorithm. So that's the reason we need to encode the data. And let's say if you're working on an image, or let's say you are working on stock market. Stock market has so many parameters in that. Let's say it has the opening price, the closing price. It has some the ups and downs and dividend and every other thing. So we don't need all of them, but we need some of them. So now let's say if there are 20 such features in the sense, if I look into an Excel sheet, there'll be 20 such columns, and there'll be a lot of rows. A lot of rows doesn't like the more the data, the better it is. But 20 such columns is like we need a 20 qubit system to to perform a classification operation. Or the, like we don't generally use uh, the example was pretty wrong, because for stock market we go for regression, not for classification. So let's go for images. So let's say image we have of 30 cross 30 size of image. So we have approximately 900 pixels. So we need 900 qubits, and that is not possible currently. We are hardly able to reach around 50 qubits. So what we need to do is that we need to encode the data in a form which is currently uh, in a dimension which is currently feasible. So that is where your this mapping function comes in. Either you can provide it here itself in the feature map, or even you can encode the data and then give it directly to the feature map. It's also possible. Then the type of quantum gates that you want to apply on your feature map will look this into the poly feature map, where we can we can apply various types of gate in various orders. And then the order of expansion. What exactly is the order of expansion? Like uh, we know that everything is a matrix. So order of expansion means, let's say if it's a first order, we take the matrix as it is. If it's a second order, we go for the square of it. The third order, we go for the cube of it. So what what are the types of feature maps which are currently available? Okay, one thing we need to be clear about is that currently everything, all the biases, uh, like the I cap and the J cap, they are in the Z plane. So that's why everything developed, the Z feature map is again the first order Z evolution circuit. Then a ZZ feature map is the second order Z poly Z evolution circuit. So all these things are around rotations around Z axis. So whereas that doesn't restrict the user to only use that. So let's say, because we know that we can develop our own biases, and then we can create a whole world out of it and represent everything in that those biases. So for that reason, we have something called as poly feature map, which enables use, which gives you the customization to whatever you want, uh, and whatever way you want to represent. So okay, the first, yeah. Now this is the Z feature map. So what exactly is this map is? Just open this up. First, I'll explain what is there inside this map. So we have a U1 gate. So what exactly is a U1 gate? U1 gate is also called as the R5 gate, which is this, I suppose. Yeah. So U1 gate is a special version of U3 gate. I can pull up the circuit for you. Yeah, this should be it. Yeah. So yeah, U1 gate is a specific case of U3 gate where the theta and phi equal to 0 respectively. Yeah, and the U1 gate is equivalent to the R5 gate, because U3 gate is a very general gate. Using this gate we can create any gate, because you just need to change the angles and provide the lambda and the phi values, and you can reach anything. So where is my system? Yeah. So here we know that e raised to 1. Yeah. We know that phi is equal to 0. So this is something which comes out as e, and then we take the whole number of it, and that is where we get the 2 out of it. So this is where the 2 comes in. And then this is basically a circuit. So it's just you apply a Hadamard operation and then a rotation around the x set, something like this is what you get. So it takes these arguments. So what are these arguments? Is the feature dimension. Feature dimension is the dimension of your features. Now let's say, as I was talking about, you take an image of 300 30 cross 30, we get 900 parameters, 900 pixels. So now let's say if I take 10 such images, let's say, okay, so 1 2 3, let's say 1 2 3, and we have till 900, and then we have 10 such images. So it will have around 900 dimensions, and we currently cannot do that. So we do a feature reduction. There are various ways to do that. You have PC and various other algorithms. So you do a reduction, and currently you try to bring it down to around 3 or 4 or 2, and then the number of rows pretty much remain the same. And then you divide this into train and test, and then how a normal machine learning works, and then you train the model on a trained data set, and then you do a validation on the test data set to check how well it is performing. So that is the feature dimension. On the reps, we here talked about the depth. So what does rep means is, now let's say if okay, I'll just copy this. Yeah. So yeah. Okay. So we have one this, and then we have one more this. So if we have rep equal to 2, that means this is the kind of circuit we are looking into, where we have the input, then we have the head amount, then we have the U1 gate, and then the H and the U1, and then we have the output. So it kind of depends on currently it's you can consider this as a hyperparameter tuning, where you need to decide how many reps you want, and yeah and yeah how many reps you want, and let's say again how many feature dimensions you want, because when once we encode the data, we are definitely kind of losing some value, some data, but it is currently required because of the constraints we have right now. And then the data map function, that is how do you want to encode the data, like we'll be discussing this when we go to the hands-on. I have an example of this, how do we encode this data. Then we have the set feature map. So it's pretty much the same thing, whereas we just have a second order, because you just change the order, and there's what by doing by changing the order, what advantage you get is you are now able to get the entanglement state out of it. So yeah, here here phi exactly is a classical nonlinear function. So what is the task of a nonlinear function? So we know that as yeah we know okay we know that this in this kind of data set which we saw in that GIF, in this GIF, that we cannot exactly create a line which can cut the divide the data set in such a way that we can separate two classes. We needed something non-linear which could try to learn the things which are not possible linearly, kind of try to approximate everything. So yeah, so there are two default values here. The default value is directly if you give x, like you give the phi value, and you get the same as inside it is. Whereas over here, if you give, there are two possible ways. If you like by default, the initial segment is pretty much this our Z feature map, whereas the next segment is the next entanglement, which creates the entanglement state. Whereas the angles, how do we get, because if you look at the U1 gate, I'll pull the documentation of the U1 gate as well for you guys so that you can have a look on that. Just give me a sec. U1 gate, yeah. Yeah. So you see this lambda going in. So what is this lambda value? That this theta value. So this is initially in the z feature map. It is exactly the same with two into that number. Whereas once we are in the entanglement state, it is two into the product of pi minus the first angle, where and the pi minus pi minus the first value and the pi minus the second value, and then you take that angle and then go inside. Here it provides you to like the entanglement states are in two forms. It's either full or linear. So it's a bit more in technical because if you want to get a gist out of it before I go to poly feature map, it's more like you have a data set. Okay, we have a classical data set. We want to represent it into an Hilbert space. So how do we do that? We have this Z feature map which takes the input. It does some gate operations in it. Uh, these are the gate operations which we see, and then the output of this is something represented in a quantum data. So that is what exactly it does. So, by the way, how people came up with these kind of circuits can be one question, which even I had in mind. But then it's more onto the research portion of it. Okay, you try out different things and then you figure it out. So that is what. So that is what polyfeature maps allows you to do that. Anyone have any questions? Okay. So yeah. So by default, polyfeature map has default values of set and zz, which one, if we don't change that, it is equivalent to Z feature map, which is this. So this is the Z, and this is the ZZ portion of it. So what here we can do is, as initially I was talking that you have various different types of ways you can represent the data. You can apply different types of gates. So here this gate represents the Z, Y, and ZZ. Okay, and this is for 2 qubits. So how do we identify whether it's for 2 qubits? We have this feature dimension. If it's 3, that means 3 qubits. If it's 2, that means 2 qubits. And the number of horizontal, the number of rows says how many qubits are there. So yep, what is polys? Polys is the list. These are the arguments that this function takes. So this is the list. What you pass it when you call this function, you pass this list as an argument, and then you get something like this. Yep. So I'll come back to this once I share a bit of my code, so that even you guys are not blown away, because it's pretty complex. I feel it's not pretty complex, but it's something new. Just finding my notebook. Okay, let's see. Collab, yeah. Okay, currently the script will be shared with you all. So this script is currently running for 19.1. Like QScript gives a lot of updates, and sometimes once they upgrade, a few things break, because it was kind of even for me to I've seen a lot of QScript tutorial on the website itself, which I run the latest version, it says, there is some kind of an error, and then you raise a ticket, you raise an issue, and then they say it will be rectified in the next version. So 19.1, I find out pretty stable to run this code to perform the QSVM operation. So that's why it's written on this. You can definitely try on the newer versions. If it fails, you can definitely come back to this thing. So, okay. Yep. So initially, if you are familiar with QSVM, or if you have done something like that before, you might have seen something called as second order expansion instead of these things, which was there in the Aqua library, qscript.aqua. So that second order expansion is the same thing as set feature map. I can pull it up for you as well. Second order expansion.
Băcătila. Please take the last picture. Older than nothing.
Do you have any questions, Amol? Okay. So now if you look at this, it says, it's depreciated. And everything can be found under polyset expansion. So, oh, sorry, it's again depreciated. So everything can be found under this thing. Qiskit circuit library, there's a feature map. It's the same thing. You have seen all these things are same. And so it's just a new name given to it with that. Yeah, so what we do is here Qiskit provides a set of data sets. You can look into this. I guess 5, 7, 8 data sets it supports. But in the end, even have shared how you can, load your own data set and then perform these operations onto it. So, yep. So what here we are doing is we are just loading the data set over here. 20 means 20 data points of each class. So for the training it's 2020, for test it's 1010. So yep, n equals to the number of dimensions. Number of dimensions we have kept it as 2. And then yep, this is just for the plotting purposes. So we plot the data set, and yeah. So this is how we it's pretty easy to represent. One is you just provide the, if you're implementing ZZ feature map, you just provide the feature dimension. Feature dimension over here is 2. So you say, okay, I need 2 qubits. Then number of reps. Reps indicate how many times you want that circuit to be. So this is more like a hyperparameter tuning that you need to figure out for your own data set which one will work out and which one will not. Same goes with the entanglement, whether you want to keep it full or linear. And then now this is kernel estimation. So that's why we are using QSVM. If it was variational quantum circuit, we would be using VQC over here. So one way to do it, you just do a VQC over here, and then it works. And then you need to provide the necessary parameters for that function call. So yep, okay, it's pretty low on the size. So it's still pretty low. Yeah, this should be working fine. Yeah. Okay. So what we try to do is we try to fit the sample ad hoc data set. This is there's a sample data set we just create a feature map, and the feature map is we have this data set. This data set is converted into the quantum space, and then initially I talked about where is my yeah. Initially, I talked about the 3 steps. When we convert the data, then we process the data, and then we apply the measurement and read the output. So the processing of the data and the applying measurement is already taken care by this guy. The in VKC we can find it a bit separate, whereas here it's everything is under this. So that means we have something called as optimizer also. What is the task of an optimizer? If I talk about in machine learning terms, the task of the optimizer is to to lower the cost, is to force the functions to be on to lower the cost function so that we can have a higher accuracy. So here also we have cost functions, whereas in QSVM it's pretty much they have already this module already has a optimizer inbuilt in it, so we don't need to explicitly specify it. And the loss function for this is something right now we cannot change, but maybe in the future we may get the flexibility to do that. So uh, so QSVM, what it takes is, the feature map, the training input, the test input, and what is the data point. Okay, the data points are, we can just do a why is it busy? Okay, it's still running this one. Okay, that's why. Yeah. So data points are the, let's say, random samples taken with let's say class related split data. Okay, this is the validation thing. Okay, there's a validation samples. And yep. So we perform the operation and we kind of get a testing ratio of 90%, which is pretty good. So this, now how do we implement the Z feature map? It's the same way how you, this is the way how we represent the Z feature map. Z feature map is pretty much the same way. We just don't have entanglement because we saw that, Z feature map is just a Hadamard operation and a U1 gate after that. So it does not help, helps us to leverage the, yes, you can see, yeah, we can see, the feature dimension over here is 3. So that's why we have this one segment, and then we have this circuit repetition as 2. That's why we have 2 blocks of such thing. So yes, so that's how we run. This notebook will be shared with you guys so that even you can, try and run at your own end and see how it works. You can try with your own data set. So this is polyfeature map. So again, now let's say if someone wants to say, why should I always work on the z-axis? Or let's say the z gate, because it doesn't give me the kind of advantage I'm looking for. Or let's say I'm not getting a decent accuracy. I tried with a lot of parameters and it's not working out for me. Can be possible. So what we do is we go for different gate rotations. We try X, Y, Z, and even you are not only restricted to U1. So if you look at the documentation of polyfeature maps, it, I had opened for you guys. I'll just pull it again up. I'll open here itself. Poly. Yeah. Yep. So, if you look at the gates, it provides you a lot of gates here as well. And yeah, it provides you a lot of gates where you can hear it, or where you can just not use U1. The reason why it's U1, because by default we know that everything is in the Z axis, so that's the reason they have kind of given the default as U1. But you may not need to do that. You can definitely have the flexibility to change these gates. So okay, for multi-class, this is very nice. For multi-class problems, there is a way on how QSVM solves it. For binary, it's pretty straightforward. It's either this or this. So for multi-class, there are different ways in which, yeah. So it has all pairs, all against rest, and error correcting code. So I'll just bring each of them in front of you. Yeah. So what does all pair says is by the way, you need to specify. If you look at the, no, back, yeah. If you look at the QSVM documentation, it says if it's a multi-class extension, you need to provide that there are more than 2 classes. So in this extension, there are 3 extensions which are currently supported. One is all pair. What it says is I'll have k into k minus 1 by 2 number of binary classifiers. So what do you mean by that? It says, let's say uh, I have 4 classes, A, B, C, and D. So it says k is 4, so 4 into 4 minus 1 by 2 classifiers. So that means 4 into 3 by 2 classifiers. That will be around by 2, it'll give us around 6. So that means I'll have AB, AC, where is it? Yeah, AC, AD, BC, BD, yeah, and then we'll have CD. So we'll have around 6 classifiers, which will say, okay, once I feed in the data, and then the model then needs to figure out, okay, it either is A or B, it belongs to this one, it belongs to this one, it belongs to this one, and then after going this, it's just a binary classification. It either belongs to this or it does not belong to that. If it does not belong to this, then one is one against the rest. So what here this segment says is that will here will be developing n classifiers. What does that mean is, let's say if there are 4 classes, we'll have 4 classifiers saying that one for and each class will have a classifier saying that if it's an A, I have this classifier which will definitely fire, saying that it belongs to this. So something like you can look something like uh, like a one hot encoded vector, saying that ki, if this is a data set which is coming in, and then it goes to let's say, hold on, it goes to a circuit, and then it goes, and then it gives an output something like that. Now we know that the first classifier was for A, so that means this belongs to class A, something like that. And then we have error correcting codes. So what is this? It says is uh, it says, let's say, okay, first I'll read out the definition to you. Um, let's say for a 6-bit for a 3-class problem, we'll have a 6-bit ECC. So what does that mean is we have 6 bits: F1, F2, F3, F4, F5, F6, and we have 3 classes ABC. For every class, once when we are training, we'll have these bits firing, saying that it can be anything. Okay, so once we do that, once we train on the on the full data set, once our training is complete, we'll have for each class we'll have a set of bits which will say, okay, let's say for A it is 0100 100, for B it is 111111. It can be anything, and then for C it can be anything. So once we are testing the data, what we do is we get we project the data to our model. It gives us this bit output, and then we do a Euclidean distance check. The one which is the closest, it belongs to that class. So that is what is yeah, that is what is the error correcting code. So if we look into a code, yeah. So here I have just different given different types of poly feature map. We have ZX ZY, then lower if we go here we have, I guess, Z by Y, then we have ZZZ. This ZZZ is the same as this. They both are the same thing. And yeah, so these are the versions which I'm running onto. So yeah, once we have a multi-class data set, now let's say now this is an iris data set. So as we know, iris has 3 classes. So we have the class A, the class B, and the class C. So what we do is here we provide, it's pretty straightforward. What you do is you give an extension and you say like qskit.aqua.component multi-class extension import all pairs, and then you provide it as a parameter, and everything else remains the same. And what it does is it runs for you and gives and trains. So now one more thing which I was talking about earlier was too many tabs open. Was going for something of, yeah. a data map function for encoding the classical data, so something like your own custom function. So here we are using that function. So what we can do is you can create your own function which takes in the input. It provides, uh, it transforms the data saying that it has to be, if the length is 1, it has to be the same number. If it's not, then what we do is we subtract pi from each of the value, and then we multi and we yeah we subtract. So we have the I value and the j value. Here we have m and n. So the x has to be a numpy array, a 2D numpy array. So and then we kind of do a multiplication of that. So something like the as we saw that pi minus xi into pi minus xj, which we had seen. Okay. So, yep, something like this. So that is what we are exactly doing over here. It was just an example to show how we can do with a custom function and then just return it. And over here, what we do is for data mapping function, we say, okay, use a custom data map function, and everything else pretty much remains the same. Now we come down to our, yeah, what exactly is the process? So we have the data set, we convert the data set into quantum data, and then we train our circuit onto that. And then what we do is we have a optimizer. What is the task of the optimizer? Optimizer task is to make sure that we have a very low loss value, like how a machine learning algorithm works. So for that, here we have three types of optimizers. We have Coblia, SPSA, and SLSQP. So by default, QSVM kernel estimator use SPSA because that pretty much gave them the accuracy they wanted, pretty good accuracy. So we will be looking into these three once we are in QVC, because right now you don't need to actually, when you're working on QSVM, you don't using kernel estimators, you don't exactly need to worry about the optimizers because it's already been taken care. Whereas once you are in QVC, you definitely need to look which one should I use and which one should I not. So yep, currently the cost function is fixed and cannot be altered. Yeah. So the one last thing which is remaining is, okay, we looked into different feature maps. We looked into, building our own custom functions to transform the data, to encode the data into the desired format we want. So one more thing is, okay, saying that, Shubham, we know that, these are all the data sets which are already there. So, but we don't have a data set onto the library which is provided there. So how do we do it with our own data set? So, okay, I don't know how many of you attended the hacker challenge where they showed us how to do that. So what it says is that there are two ways to do that. One is, okay, I'll just open it for you. I hope it opens. Yeah. So the first column represents the label. This challenge was to classify. It was an MNIST dataset where the dataset was only of about for class 4 and 9, and all those 784 elements. So how 784? It is 28 cross 28. Each image was 28 cross 28 pixels, so that gives us 784. Now, as we know that we don't have the correct capacity to go for 784 qubits, because the number of features represents the number of qubits we require. So that's why we did an encoding on the top of it, and a conversion was made to three features. So this is what everyone needs to do. What let's say if you're working on any kind of data set, whether it's images or whether it's any data set in CSV format, what we need to do is we can even use PCA. Let's say we get the data, we perform a PCA over it, principal component analysis. We reduce the dimensions, we get it around to 2, 3, 4. Currently, it is supported till 3, so we can get it around 2 and 3. The current user supports till 3. So we can get it around 3, and then what we do is we store it in a CSV, or we can even we store it in a CSV, and then we load it as a NumPy data, and then we split the data. So as you have seen over here, our data set pretty much looks like we in a dictionary we have a class followed by an array of data points, then a class, then an array of data points. This is how is the format of how QSK takes in data. So that is the format we need to generate as well. So how do we do that? We first split the data labels. These are the data labels, and then we get the features out. The rest two, three, four columns. There's just a plot, like how the data set looks. Can we look at yeah? So yep. And then what we do is we have these data features, the features we extracted from them. Okay, we because we created the data set, we know key the first 1,000 points belong to this class, the next 10,000 points belong to this class. So what we do is we randomly select. Here the data set was around first 3,000 were belonging to 4, the next 3,000 to 6,000 was belonging to 9. So because on this thing I worked on a sample of a data set which was 1,000 points. So what I did is was from these, sorry, so from these 3,000 points, I randomly selected 1,000 points. Same goes with this thing, and then so here we extract those 1,000 points. We convert those 1,000 points into arrays, and then we do the splitting of it. That means out of 1,000 it will be 800 and 200. So we get the split, and then because we are using a random default generator class, so that means all these points will be random. So kind of we have a very shuffled data set, and then we split the training and the test data set. And once we do that, it's just you need to take two classes A and B, and like how we had over here, just create a dictionary out of it. We have a class, let's say C, and followed by it's a key value pair. So we have, we take a class A and then a B, class B, and then the following train data set and the train data set, and then the test and the test. And pretty much the lower one pretty much remains the same. Right now it was running for pretty long time because, you know, the this feature operation is something which is not at all good on a classical computer, because right now the dimensions are less, but it takes a while to perform those, and right now the data set is big. So all these operations when done on a quantum computers are much faster as compared to classical computers. So even run on a simulator, the backend is itself a classical computer, so it doesn't really gives us the speed advantage. So that's why it was taking a really long time. So yep, you can definitely run it, keep it for some amount of time. It'll give you an output, and yeah. So that's it. So in this way, we covered. I'll just give. Where is that? So I'll just do a small summary of it, so that everything is pretty much straightforward for you guys. And so we looked into what is SVM. It converts the data into like it classifies you with the help of hyperplanes. We know as the number of features and the dimensions increases, SVM are not very good classifiers. So so we need quantum SVM so that we can remove, or we can get rid of that weakness. So how to do that? We have three steps. We convert the classical data to quantum data, then we process the data, and then we apply measurements to read the outputs. So to to convert the data, we have quantum feature maps. There are four things we need to look into mind, which is the depth, number of the sockets we want to attach, then how do we want to encode the data, then what kind of gate operations do we need, and what is the order of expansion. So in that we looked into the different types of feature map. We have Z feature map, ZZ feature map, and if you want to go into something more general, we have poly feature map that gives you the kind of flexibility to go into to use any gate. And then For multi-class problems, we have few extensions which are provided. The one pair, one against rest, ECC, one pair. We generally form k into k minus 1 by 2 binary classifiers. For one against the rest, we form, let's say n is the number of classes. We have n classifiers. For ECC, we have bits, and using those bits, we kind of form a code. And then when we are testing, what we do is we find the distance between those codes, and we then the shortest one says it belongs to that class. Then we have the classical optimizer. The task of the optimizer is to reduce the cost. In QSPM, we use SPSA, but what exactly SPS is and what exactly are the rest of these things are, we'll be looking more into depth in PKC. And yes, and then we looked at the implementation of it. We looked at how we can implement it for multi-classes, how we can load it for our own custom data set. So yeah, that's it from my end, guys.